In this Petri Net model, who decides which traffic light turns green next? Hi, my name is Andreas Henz and I make videos on business process automation. Today I'll talk about two related topics on Petri Nets: non-determinism and fairness. The motivation for this video came from two important viewer questions, both on the traffic light Petri Net from the introduction. Life of Sadat 368 asked about which transition fires next, and Piggy TV correctly noted that the traffic light Petri Net lacked fairness. Before we speak about non-determinism and fairness, we need to dive into the foundations of Petri Nets. Don't worry, this won't be too hard actually. As long as a Petri Net is not dead, there are always one or more transitions that can fire. Which transition actually does fire and when is decided by the environment. When we play the token game in Woped, we are the environment and click on certain transitions at any time we choose. Our interactions with the Petri Net result in a so-called firing sequence. Firing sequences are simply words over the alphabet of transition names. Each Petri Net defines a language that contains all firing sequences that can be created using it. So here the traffic light Petri Net with its initial marking. There's one token in red 1 and one token in green 2. So if we have, for example, the firing sequence F, E, D, we get back to the same marking as we started with. But if, for example, we have the firing sequence F, E, C, we end up with a marking where the traffic light on the right-hand side is red and the traffic light on the left-hand side is green. Each Petri Net with an initial marking also defines the set of all markings that are reachable by firing sequences from this initial marking. For our traffic light Petri Net, the marking where the places GR1 and GR2 both have a token at the same time is not reachable. This marking would correspond to the state where both traffic lights are green. The nice thing is that we can automatically prove that this marking is not reachable and therefore prove the traffic safety of our Petri Net. Back to our environment. In practice, we don't have any gnomes sitting in control cabinets playing the token game. Instead, we can imagine that the control cabinet contains a circuit board with integrated circuits and timer modules that are wired to a component that contains the Petri Net. The non-determinism of our Petri Net is resolved by the environment making the choices. The current Petri Net can be used for several scenarios. First, alternating traffic lights that always go like green for east-west, then green for north-south, green for east-west, and so on and so forth. Second, induction loops. In the normal state, both are red. When a car approaches from the east, for example, the corresponding traffic light turns green. After a while, it goes back to red. Third, it could even be that scenario 1 is used during the day and scenario 2 is used at night. All the magic happens in the control cabinet. The Petri Net simply guarantees traffic safety. Now to our second point, fairness. In our traffic light Petri Net, it would be unfair if only the traffic light on the right-hand side would turn green and yellow and red all the time, but the traffic light on the left-hand side always remained red. The current Petri Net does not guarantee this fairness. As we have seen in our three scenarios, we can still have this fairness built into our environment. As Piggy TV pointed out, we can easily modify this net to guarantee fairness on its own. We can implement strict alternation. So this is our modified Petri Net. As you can see, we have two additional places. One is called turn right and the other one is turn left. And the initial marking is again, we have a token in the red place on the left-hand side and in the green place on the right-hand side. And now if we start changing, so we have F activated, then we have E, and now both traffic lights are red. And now because we have this additional place which is called turn left, there's only one transition activated now, which is C. And if we activate C and then B and A, we get to the situation now where both traffic lights are red again, but now we have a token here in turn right, and then we go with D back to the original state. And this goes on in a circle all the time. Note that the resulting Petri net is now deterministic. There is always exactly one transition activated. Thank you for watching.